Three, two, one. Welcome to this lesson 1.3 on elemental composition of pure substances. And so in this lesson, we're going to explain the quantitative relationship between the elemental composition by mass and the empirical formula of a pure substance. So let's just review what matter is. So matter, oftentimes we can kind of classify that as two types, either a mixture or a pure substance. Oftentimes, if we can see that there's multiple compounds or multiple substances, we know that's a mixture. Or if we know that in this matter there are different types of compounds, then that's a mixture as well. Okay, so if we can see that there are different things in this mixture, then we call that heterogeneous mixture. If we can't see, but we know that there's different compounds, such as if I look at tea, I know that inside tea I have water, I have the coloring, I have the different antioxidants, I have all the different sugar, okay, or even milk mixed into my tea. So when I look at my tea, it looks the same, but I know that inside I have many different things, then that would be called a homogeneous mixture. Now, if inside my matter I only have one type of thing, one type of compound or one type of element, then that is called a pure substance. Okay, so once again, a pure substance means that inside this amount of matter, I only have one type of element or one type of compound. So if it only has one type of element, then that's an element. If I only have one type of compound, then that's going to be a compound. And so an example of a compound is water, because inside my water, I only have water molecules. Okay, so these water molecules, this is not an element because a water molecule is made from hydrogen and oxygen, H2O. But if I have a silver rod, this is an element because in my silver rod, the only things or the only atoms that I have are my silver atoms. Okay, so to recap here, an element is defined as a substance that cannot be broken down into any other substances by chemical means. Any single element is comprised of only one type of atom. These elements are organized and displayed on the periodic table. We have compound, and compounds are formed when the number of these elements bond together. Compounds always have a fixed composition of atoms, meaning if I have water, H2O, it's always going to be two H's, two hydrogens to one O, one oxygen. Okay, so H2O. Homogeneous mixtures, these are uniform in composition throughout a given sample, but with a composition and properties that vary from one sample to another. For example, a solution of salt water taken from different bodies of water in different locations might have different amounts of salt content. Okay, so the composition of properties may vary, okay, but when we look at it, we don't see the different compounds. When I look at salt water, I just see this liquid. I don't see the salt in it, okay, mixed with the water. Heterogeneous mixtures have separate distinct regions within a sample with a composition properties that vary from one part of a mixture to another. For example, a chocolate chip cookie. And that's because when I look at a chocolate chip cookie, I can clearly see the different things. I can see the chocolate and I can see the rest of the cookie. Okay, so with that, we come to kind of the topic today on empirical and molecular formula. So a pure substance, if I have a pure substance, that means that this substance has constant composition. A pure substance can either be an element or a compound. When dealing with compounds, you can assume it follows the law of definite proportion, which states compounds with the same elements in the same proportion are the same element. So this is what I was talking about, water. Anytime you see H2O, that is going to be water. Okay, if I look over there and I see two hydrogens with one oxygen, that's going to be water. If I look to the other side and I have another compound with two H's and one O, that's going to be water. Following the law of definite proportion, you can find a percent composition, which is the percent by mass of each element that makes up a compound. Okay, so we can figure out kind of the percentage by mass of the hydrogens of the oxygens. And so to do that, there's a few steps that we need to follow. Okay, so to calculate the percent composition, you divide the mass of each element in a compound by the total mass of the substance. In compounds, the empirical formula represents the simplest ratio of one element to another in a compound. The molecular formula represents the actual formula of the substance. So for example, glucose has a molecular formula of C6H12O6. Okay, that is the actual formula of glucose. But we can reduce that because all those three subscripts are divisible by 6. Okay, so when we reduce kind of the molecular formula, what we get is the empirical formula. Okay, so if I divide 6 by 6, I get 1. If I divide 12 by 6, I get 2. If I divide 6 by 6, I get 1. Okay, so the empirical formula for glucose is CH2O. And so when we're doing calculations, these are kind of the rules and these are the guidelines and steps that we want to follow. Okay, so number one, we have to figure out what is the empirical formula before we can figure out the molecular formula. So to figure out the empirical formula, we're going to assume that we're given 100 grams of the sample, so we can easily convert kind of the percentage to grams. For each element, we're going to use grams. We're going to take the grams, the mass, and divide that by the molar mass to get the moles of each element. Okay, then we're going to divide each mole value by the lowest of the values. Okay, and if we are within 0.1 of a whole number, we're going to round it to a whole number. And if it isn't, then we're just going to multiply by a factor until we get whole numbers. Okay, and once we have these whole numbers, then that becomes the subscripts for each of the element. Okay, so that's a lot of steps, but let's take a look. Okay, so example one, a certain sugar used in treating patients with low blood sugar has the following chemical compositions. Okay, so this sugar has 40% carbon, 6.7% hydrogen, and 53.3% oxygen. Okay, and this is by mass. And so what is the empirical formula? What is the lowest reduced formula? Okay, so let's list out what I have. I have carbon, hydrogen, and oxygen. Okay, so following these steps, in step 1A, we're going to assume that we're given 100-gram sample. Okay, so we can convert all these percentages into grams. Okay, so 40%, okay, 40% of 100, this is going to be 40 grams. 6.7, it just becomes 6.7 grams. And then 53.3 just becomes 53.3 grams. Okay, so that's A. We're just going to convert it to grams. Then in B, we're going to take the grams and we're going to divide by the molar mass. Okay, so 40 times 1 over, same as divide, 12.01. Okay. Same thing, 6.7, we're going to multiply that by 1 mole over its molar mass. Okay, for oxygen, 16.00 grams. Okay, so if we do that, this becomes 3.33. This is 6.65. This is 3.33. Okay, so that's A done, B done. C, we're going to divide each mole value by the lowest of the values. Okay, so notice I have a 3.33, a 6.65, and a 3.33. So the 3.33 is the lowest one. Okay, so I'm going to divide everything by that, the 3.33. When I do that, this becomes 1. This is about 2. This is about 1. Okay, C is done. D says if you are within 0.1 of a whole number, round it to a whole number. Okay, which we did, 1, 2, and 1. And so these values here, this is going to be the subscripts of each element, meaning from this I have 1 carbon, 2 oxygen, or 2 hydrogen, and 1 oxygen. Okay, so this is the empirical formula, meaning this is the most reduced formula. Okay, so that is the empirical formula. Now for us to find the molecular formula, which is step 2, there are a few more rules. So first of all, we're going to find, typo here, this is the molar mass of the empirical formula. And then in step B, we're going to take the molar mass of the molecule, divide that by the empirical formula mass to find the factor. Okay, and then we're going to multiply all subscripts in the empirical formula by that factor. So let's take a look. So first of all, if I have my empirical formula, CH2O, okay, this has 1 carbon, 2 hydrogens, and 1 oxygen for a total of 30.03 grams per mole. Okay, so this is the molar mass of my empirical formula. But notice how this does not match the molar mass of the actual compound, right? The actual compound is 180 grams per mole. So if I take 180 grams per mole and I divide that by the 30 grams per mole, okay, then I roughly get about a factor of 6. Okay, so this factor of 6 tells me that my empirical formula is off by a factor of 6. Okay, so if I put that factor in, then I get C6H12O6, which means this is my actual molecular formula. Okay, so let's try another questions with the same kind of type of calculations. Okay, so this time a compound is found to contain 56.6 carbon, 7.11 hydrogen, and 36.4 phosphorus. Find the empirical formula. It's the same thing. I have C, H, and P this time. In step 1A, I'm going to convert each of these percentages to a mass. So this is now 56.5 grams, 7.11 grams, 36.4 grams. Multiplied by 1 over the molar mass. Okay, so for carbon, that means I have 4.7 moles. For hydrogen, this is about 7.05 moles. For phosphorus, this is about 1.18 moles. Okay, so we find the least, it's kind of the smallest number of moles, which is the 1.18, and we're going to divide everything by 1.18. And so that becomes 461, and this tells me that my empirical formula for this compound is going to be C4H6 and 1P. Okay, so once again, this is the empirical formula. And so if I want to find the molar mass of the compound, or if the molar mass of the compound is 170.14 grams per mole, what is the molecular formula? Okay, so the first thing I'm going to do is I'm going to check what is the molar mass of C4H6P. Okay, and if you do the math, this is about 85 grams per mole. Looking at the molar mass of the compound, okay, so this technically should be about 170, but I only have 85. Okay, so this is about a factor of 2 that's missing. So therefore, if I take my empirical formula, I factor in the 2 that's missing, that means my molecular formula is going to be C8H12P2. This is my actual formula, my molecular formula. And so that's it for this lesson here. If you have any questions, please make sure you email me. Please try some of these practice questions as well as the fun sheets.